Well, hello and welcome back. So we had started talking about integrals of complex functions in the last video. So before continuing with this, with the topic of integrals and broadly the four questions that we had talked about, in particular, what does the integration of a complex function physically mean? Let's sort of discuss another very interesting idea, which is that of complex mappings viewed as vector fields on the complex plane. So if you recall some of our previous discussion on the very nature of complex mappings and how do you depict them, essentially we have four variables, right? The complex variable z has x and y components, and when we have a function of a complex variables, we have two more fields, u and v. And so essentially we have four variables, and then in some of the previous videos we talked about how sort of to think about plotting or graphing these complex functions to get something meaningful out of it. And one of the ideas we briefly talked about was to view a complex function as a vector field in the complex plane, but we didn't really elaborate much on it. But now we'll see that how that offers a very, very vivid and interesting description of complex mappings, essentially which covers the whole complex plane, as well as the fact that this description will lend itself very beautifully and give a very beautiful meaning to complex integration, which will lead to many new insights about the nature of complex integration and about the nature of complex mappings themselves. So let's talk a little bit about this idea. So essentially, it's just the fact that when we define a complex function of a variable z, let's say, we have two components: the real component, which we typically denote with the variable u, which is a function of x and y, plus I times the imaginary component, which we denote with the variable v, which is again a function of x and y. And if you think about this, then these two can be thought of as two components of a vector field u comma v. So let's say we draw our complex plane, the z plane. So this is the real part of z, and this is the imaginary part of z. Then what we're essentially saying is that on the z plane, at any point x comma y, if we draw a vector associated with which has two components u and v, we can think of the x component of that vector being u and the y component as v. If we draw a vector, then that is the representation of the complex mapping, or what the complex mapping, or what the value of the complex mapping is at some point x comma y. So let's say we are here at x comma y. Then u will have some value here, v will have some value here. So we just associate with u the x component of a vector and with v the y component of the vector, and draw an arrow of the arrow which has magnitude. The magnitude of this arrow is essentially root of u square plus v square, and the angle that this arrow makes with the x-axis is nothing but the arc, the tangent inverse of v over u. So that's the basic idea of how we think about how we associate a vector field with the complex function. So let's take a specific example which will make these ideas somewhat clearer. So let's say we talk about the complex mapping, the identity mapping, which is wz equals z. Okay, so here we have a u component plus a v component, and in this case, since z is x plus iy, which is equal to u plus ib in this case, then u is essentially the u at some point x comma y is essentially the value of the point x itself. It's just the x coordinate, whereas v at x comma y is just the y coordinate. So how do we draw the vector field associated with this function? Well, we go to the point x comma y. So let's say this is x, and then this height is y. So we reach this point, and at this point we draw another vector which has magnitude, again, square root x squared plus y squared, which will be the same magnitude as the length of this vector. So we just draw another vector here and pointing in the same direction as this vector, because essentially u is just z. The only difference being that if we were to plot the complex variable z, we'll start from the origin and draw an arrow like this, just like the way we're drawing here. But now since we're plotting the function at the point x comma y, we'll draw an arrow starting at the point x comma y of magnitude square root x squared plus y squared. So the magnitude of this is square root x squared plus y squared, and this angle is tan inverse y over x, right? Okay. So what if now we draw these kinds of arrows all over the complex plane? So we'll see that, let's say this was the point x comma y. Now as we move in the xy plane, let's say we were to draw an arrow somewhere. Let's say we move along this circle and we were to draw an arrow somewhere here. Okay. So this will be an arrow here will be of the same magnitude as this, except that the direction has changed. So we'll draw another arrow which will look like this. And likewise, if we move along these circles, we'll keep drawing arrows in this form. So that's one set of arrows that we draw, let's say, around this circle. If we move along, let's say, let's say we move along a circle where the magnitude of the arrows does not change, only the direction keeps changing. Now we can move closer to the origin, and then if we draw an arrow somewhere here, then as we can see, the magnitude or the length of this arrow will be somewhat shorter. However, if we are drawing an arrow which is pointing in the same direction as this, then we'll have an arrow which will look like this. So this is at some point x comma y, which is somewhat closer to the origin, such that the angle that this makes is the same as the angle that this longer arrow makes. So that's one choice of how to draw the arrows. And then if we keep drawing these arrows, we'll draw shorter arrows in this form. Something like this. And then as we move away from the origin, the length of the arrows will keep increasing, because the magnitude of z keeps increasing as we move further and further from the origin. Okay, so that's one set of arrows that we can draw for the complex mapping wz equals z. And this is essentially the vector field associated with the complex mapping wz equals z. So let's take another example, which will be somewhat will need more insight into what we are essentially doing. So if you recall, we talked about the inversion mapping wz equals 1 over z. So how do we draw a vector field associated with this complex mapping? So first of all, again, we have to identify the real and imaginary parts of this complex function. So in this case, if we write this as u plus iv, then we can simplify 1 over z like we've done before. I'll put a link to the video where we've talked about the inversion mapping. Essentially, 1 over z can be expressed as 1 over x plus iy, which is u plus iv. And then we can simplify this expression, or divide the numerator and denominator with x minus iy to extract the real and imaginary parts of the complex function. And this will give us x divided by x squared plus y squared, which is nothing but mod of z squared, but let's just write it as x squared plus y squared, minus I times y divided by x squared plus y squared. Okay. So this gives us u is x divided by x squared plus y squared, and v is minus of y divided by x squared plus y squared. And drawing a vector field associated with this complex mapping essentially means at any point x comma y, we'll draw an arrow whose magnitude is square root u squared plus v squared, where we know the values of u and v at any given point x comma y. And likewise, the angle that it makes is tangent inverse of v divided by u. So qualitatively, what kind of a plot do we expect to get out of this kind of a mapping? Well, just write these expressions again here. So So again, we draw the complex z-plane. This is the real part of z, and this is the imaginary part of z. Okay. So now, one of the things that we can notice from this complex function is that as we move closer and closer to the origin, the magnitude of the arrows will increase. And that's because wz is essentially 1 over z. A simple way to see that is if you write this in polar coordinates, then 1 over z is nothing but 1 over the magnitude of r times e to the power of I theta. So as we move closer and closer to the origin, the value of r decreases, so 1 over r increases, and therefore the length of the arrows as we move closer to the origin should increase. But what about the direction? The direction we can notice from the u and v components here. So if we are in the first quadrant where x and y are both positive, then we can see that v is negative, whereas u is positive. So the direction of the arrow will be something like this. So let's say we are somewhere here, then the direction of the arrow will be something like this. Because x is positive, whereas v is negative. If we move further away from the origin, the length of the arrows will decrease, like this. Okay, and then if we are, let's say, somewhat parallel to the x-axis, then the v component is essentially 0, so the arrows will look something like this, with the length decreasing as we move away from the origin, and likewise this vector field will look like this. And if we are parallel to the y-axis, then again the x component is nearly 0, whereas this is minus of, this will point towards the negative y-axis, so the arrows will look something like this, and again decrease in length as we move away. So we can draw a sequence of arrows which look like this. If we are in the second quadrant, then here again y is positive, whereas x is negative. So since x is negative, and for a positive y, v is anyway negative, so u and v both components will be negative, which means that the arrows will tend to point in this direction. And it will be symmetric, so we'll end up drawing something like this. And a very useful way to sort of visualize these things is actually on the computer. Like if you just plot this vector field on using some software, it'll give a very easy and quick way to visualize a lot of complex mappings. Likewise, in this quadrant, we can figure out that the arrows will point in this direction. And in this quadrant, they will end up pointing in this direction. Okay, so we'll get a sequence of, we'll get a vector field for 1 over z, which will look something like this. And this is a very interesting example to keep in mind, and we'll talk about this a little bit more as we go along. Another interesting example that is very useful to talk about right now is associated with this particular complex mapping, which is wz equals 1 over z bar, or the conjugate of z. And in this case, just like the algebra we just did, the u and v components, the u component will essentially come out to be x divided by x squared plus y squared, whereas v will be y divided by x squared plus y squared. And the difference between 1 over z bar and 1 over z in terms of the vector fields is that 1 over z had a v component which is negative of y, whereas 1 over z bar has a v component which is positive of y. And this yields a very different kind of a vector field that looks very different. So in this case, so again, this is the real part of z and the imaginary part of z. Now, if we are in the first quadrant, both x and y are positive. So the arrows will point. So if you're at some point x, y, then the arrow will point in a direction where x and y are both positive. And just like the 1 over z mapping, as we move closer and closer to the origin, the length of the arrow keeps increasing. So essentially what will happen is you'll end up getting arrows which look like this. Okay, so as you can see from here, this plot looks qualitatively very different from the plot for 1 over z. And again, a very plotting these on a computer will actually be very, very helpful. One software that one can use, which is openly available, is the software Octave. It allows for very easy plotting, and so it's a good way to get a hands-on experience of these kinds of vector fields. Okay, now so it's probably not drawn very well, but essentially the idea is that the length of the arrow keeps decreasing as you move away from the origin, whereas the direction is sort of somewhat similar to that of the mapping wz equals z. So the direction of the arrows is similar to that, but because essentially the direction of the arrows will be tangent inverse of v over u, the denominators will cancel out, and it will again give you y over x. So the direction of the arrows will be very similar to 1 over to the mapping wz equals z. However, the length of the arrows in this case keeps decreasing, whereas for the mapping wz equals z, the length of the arrows kept increasing as you moved away from the origin. Now this vector field will sort of remind you of some very physical something that you come across when you study, let's say, electrostatics or two-dimensional fluid flow, and as you can see here, we can think of this as some kind of if you think of it from the point of view of electrostatics, you can think of a source of positive charge here from which an electric field is emanating out, and as you move away from the source, the strength of the electric field keeps decreasing. And it's sort of radially symmetric about where the electric field is located, so it's sort of moving in this radial pattern. Oh, sorry about that. Right? Whereas the strength is decreasing as you move away from the source. Likewise, you can think of this as a source of fluid in a two-dimensional plane where there's some, let's say, water coming out and it's moving away radially from the source of the flow. And that's one of the reasons why this particular mapping, wz equals 1 over z bar, is said to represent a source. Which physically physically represents a source because of the way the vector field looks like. Now, likewise, if you draw the vector field corresponding to the function wz equals minus 1 over z bar, then we'll see that the vector field essentially looks the same, except that the direction of arrows is reversed at every point. So in that case, we get a vector field which will look like this. So now the arrows are moving towards the origin. Okay. And again, it has the same radial symmetry as that of the source, but in this case we see that the fields are converging towards the origin. And this can represent from the point of view of electrostatics, this can represent a negative charge, a source of negative charge where the electric fields converge. Or from the point of view of fluids, we can think of this as a sink. Let's say if you think of a washing sink where we wash our utensils, for instance, the water from all around the sink sort of flows into the drain at this particular point. And so this kind of a vector field is associated with something that's called a sink. And essentially you just get the sink by considering the vector field for the mapping wz equals minus 1 over z bar. And a source you get when you consider the mapping wz equals 1 over z bar. So these are some examples of how to draw a vector field associated with a complex mapping, and in particular the idea of a source and a sink is extremely useful when we start thinking about what is the physical meaning of integrals of complex functions. So we'll come back to these ideas again. This was just this video was sort of just to get us motivated in how to think of complex mappings as vector fields, and we'll see where they sort of come into our discussion of complex integrals very soon. So hope this was of some use, and hope to see you soon. Thanks for watching.